Alright, in this video we're going to be talking on Mesomeric effect or conjugative effect and steric effect or steric hindrance. Now in my previous video I actually talked on inductive effect and electromeric effect. Now this is like the continuation of that video because actually these are the remaining two effects that actually affect bonding in organic chemistry. Now let's start with the first one, conjugative effect or mesomeric effect. Now this only occurs in compounds that are conjugated. It's only found in compounds that are conjugated. Conjugated compounds are compounds which have alternating single and double bond and have the localized pi electrons. Now the next point says that is compounds with resonating single bonds or double bonds, or simply a sigma bond between two pi bonds. That's actually what we know, or what we call conjugated bonds and so on. Now these compounds can be represented by different canonical forms. Canonical forms are like the different structural representations, and the sum up of all canonical forms give a hybrid form. But in general, a hybrid form can be used to represent like the sum up of all the canonical forms. The canonical forms show the different orientations of the resonating single and double bond, like I said earlier, while the hybrid form shows the true orientation of the bond. The hybrid form shows like the general orientation of the bond, while the canonical form shows the bond position at a particular time, which can actually be changing with time and so on. Now, I also want to give like a structural representation of what I mean by conjugated bond. Let me just give you an example. We all know benzene. This something like this. We all know benzene, which can also represent it by this, a big circle. But this is not the structure we're actually looking for. I actually want to show you the canonical forms, so let me not actually use the structure. Now this form is benzene. This is what we all know as benzene, but we know that benzene is actually always undergoing resonance. That means this form is not actually permanent form. This is actually like a more of a temporal form than a permanent form, because these pi bonds, they are delocalized. What I mean by they are delocalized is that they are not steady in that same position. If it was not delocalized, something like alkane, or what should I say, I can have something like cyclohexane can also be like this. I can have 1 3 5 cyclohexane. It will actually be like this, but the major difference between that and this benzene is that the cyclohexane, the 135 at the position of the double bond, they are always steady, while this you can never see one or whatever in benzene, because the electrons, they are always moving. Actually, we actually have a different method of naming them, and I'm sure you've already learned of it before. Now, like I said earlier, these pi bonds are delocalized. That means this bond can actually move here, this can actually move here, and this can actually move here, giving it another form, something like this. And therefore we have something like this. Now if we look at it, these two forms are actually different. They are not the same, because the pi bonds have actually moved from one particular position to the other particular position, but it's still the same benzene actually. Now these two bonds, we can call these two forms, we can call them canonical forms. It can be found in benzene. It can also be found in other compounds. There are rules for conjugation. Actually, we can actually talk about that later on, because if I start going deep into that scope right now, it's not going to be part of the effect I'm actually talking about. The effect I'm actually talking about is conjugative effect, and that is actually this form, like the alternating single and double bond. So it's not actually part of the syllabus. I might talk about resonance and all those other stuff later on. And now these are the canonical forms. So I can actually give a hybrid form like the structure I drew earlier. To avoid the stress, just put a circle here. This is like the hybrid form. Some people actually, instead of using a full circle, they actually use lines, or like something like this. Something like this. They actually use this to represent the hybrid form, and that's just like the conjugated form. Now, the second form, like I said earlier, is the steric hindrance, like the second factor, or what should I say, the last factor affecting bonding in organic chemistry is steric hindrance. So we're actually going to be talking on steric hindrance right now. Steric hindrance is also called steric effect, and this is due to the presence of bulky unreactive groups surrounding the functional groups, thereby increasing its reactivity. I mean, decreasing its reactivity. Now, just like if I want to like use what should I say, grammatical example, like just like you're in a crowd and you want to actually say something, but you're surrounded by people are actually not actually making sense. They're just saying rubbish and they're all shouting, and you are actually at the top of your voice, but your voice is not loud enough, so you cannot actually like attract an external member down there. So that's just like an example. That's actually what's happening to the carbon atom here. These unreactive groups might include methyl, ethyl, and so on. An example of this can be seen in aldehydes, ketone, and ketones reactivity. Due to this effect, alkanals are more reactive than ketones. If I put it down, aldehydes are more reactive than ketones due to this effect. Now, let me just actually like give you an example. Then I'll actually talk on this, and this is what I'm going to end the video with. But let me give you an example. Let's say carbon. I want to compare two carbons. Now, the first carbon is surrounded by hydrogen. The first carbon is surrounded by hydrogen. This hydrogen, they can't actually affect the reactivity of this carbon. This carbon, as we see now, it's going to be like, this is methane. It's going to be more reactive than a carbon surrounded with like four different. Let me just give you the second example. This methane is actually going to be more reactive than a carbon, something like this, surrounded with C. I'm actually going to draw the entire branch structure so you can actually see what I'm talking about here. CH, 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 another C, H, H, and H, and the last C. Oh, this is not the last. H, and H, and then another C, H, H, and H. Now, if you look at the first structure, the methane structure, and you look at this structure, imagine like an attack, like what should I say, an attacking group is actually coming to like bond with this carbon. Before you can actually get to this central carbon, let me give it a different color. Before you can actually get to this central carbon, how many bombs does it have to take? It has to like bomb this first group. You can actually bomb this second group, actually come here, bomb this third group, or actually go and bomb this fourth group. And that will actually, like the space for it to actually come and bond is not there again. And these groups are unreactive groups. It's not like they react and form another complex or something like that. They are unreactive. Therefore, they reduce the reactivity of this carbon. Now, if we are naming this carbon, we can actually have this is 2,2-dimethyl 2,2-dimethyl propane. So we can actually look at this methane and 2,2-dimethyl propane. We find that methane will actually be like more reactive than this because of it's not because of like the length of the name or whatever. It's actually because of the bulky group, and this effect is called steric effect or steric hindrances. Now, I said I'm actually going to be talking on aldehydes and ketone. Now, this is a very common example. Like aldehydes, we all know that they are more reactive than ketone. Why are they more reactive than ketone? It's not due to secondary or whatever. It's actually due to steric effect or steric hindrances. Now, we all know an aldehyde, something like this: R, C, double bonded with O, and single bonded with H. This is an aldehyde, or what should I say? This is like structural representation of an aldehyde. So I can actually call this aldehyde or alkanal. Now, I said this aldehyde will be more reactive than a ketone. Now, if you look at ketone, RC, I'm actually going to open all the branch structures so you can actually see C, H, 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 or I'm just going to use like, let me not use H, let me just use an R so it can actually be better and well understood. Okay, this is an R, but I'm actually going to be putting on my bulky H, something like this. This is the group. It's not normally meant to be like this, but I'm just actually trying to show you that maybe it might not actually be a methyl group, it might actually be other functional groups. So now this is my ketone or alkanol. Or alkanol. Now if we look at this, one hydrogen present here, and we can see an R group. This R group can go up to C100 if I put it that way. It can reach C100. And now imagine if it's C100. How will any like attacking agent, or should I say an attacking group, come and attack it? It can't attack it well. It will actually bomb and bomb and bomb, and reactivity will actually decrease because of that. And that's like the major reason why we normally see when we're actually testing for the difference between aldehydes and ketones, like we see whenever we're testing for it, you always see that it's the aldehyde that reacts. The ketone ends up not reacting, not because it's formed by a secondary alkanol or anything. It ends up not reacting because of this effect, this steric effect. It ends up decreasing the reactivity. It's always like the last to react, and that's like how we actually differentiate between both of them. Now that is all about steric effect or hindrance. Thank you for watching this video. Please like and subscribe to my channel.